and N region, right? So
yes, sir.
So let me draw a particular circuit, right? So there is some plate in this way, and then we have another layer of N-type material, and then we have P-type material. P-type material. So in the practical solar cell, what is happening? N-type is very thin, right? This layer is very thin, and it is heavily doped as compared to this P-type. This is very thin, so that whenever the light intensity of light falls on this, they can form a depletion region in between these P and N-type. So we have to increase the depletion region area, where as soon as the lights are falling, it starts emitting the electrons, and doping is also necessary to increase the electrical conductivity in between these two panels. Right. So as soon as we have these holes and electrons in N-type and P-type of material, so they are going to recombine at this stage. Right. At this, we have some holes like this, which is recombining with the electrons. And at the same time, we have some free electrons as well, which will cross this depletion region. Because you will send some energy through this. So some electrons, free electrons, they will go to here. And due to this free electrons, if you have connected some electrical circuit here, so current starts flowing in this circuit. That is the basic principle. As the photons fall on the surface of solar panel, and these free electrons, they have this very high energy. So they will cross this depletion region, right? And once it is connected with the output circuit, if this is open, there is no flow of current. But as soon as you are connecting some external circuit, so current starts flowing, or these free electrons, they are flowing through the circuit. This is the basic principle. Through the wire, and current starts flowing from this. The closed path will be created, because this is also on the same ground, and this is also connected with the same. So due to these the electrons which are cross this depletion region, they have some energy, right? And they will be having.
Thank you, sir. Thank you so much.
Yeah.
Thank you, sir.
So this is the basic principle. Due to N-P type of material and due to free electrons, the energy, and you have connected some external circuit, so current is flowing in this way. Okay. So we were discussing about this IPV and PPV. So this 10 kilowatt panel, we have to see, and what would be the intensity of light, and what would be the function of this, we have to see. So if I'm saying we have installed a 10 kilowatt panel, that is installed capacity, right? That is installed capacity. That is not the actual capacity for which we are supplying the power, because the efficiency, or there is one important parameter that is known as fill factor, right? So fill factor, and in this particular characteristic, there are two mode parameters, right? Two mode parameters means parameters and this. So this is IPV, and this is PPV, and this is the okay. So this will be wrong, because we have to have this. So we have to draw this very closer to this, so that this peak point should come into the picture. Let me redraw it again. So this is, so here we have two main parameters. Suppose this is representing IPV and this is representing VPV. So we have two main parameters. Now this point, so this is representing your open circuit voltage, and this is representing the maximum possible current of a panel, right? Maximum short circuit capability. This is the maximum current. So initially I told you a panel has 8.3 and 32 volt. That is the open circuit and short circuit, open circuit voltage and short circuit current. So these two parameters, generally VOC, we are representing as a open circuit voltage of a panel. ISC, short circuit current of a panel. There are two main terms, right? If I go to the MPPT, So this is the maximum voltage. But as soon as I'm approaching to the maximum point means this is the point where we are getting the maximum power. This point it is known as VMPP, right? VMPP or VMP simple you can say. And at the same time, the magnitude of current at this point that is represented as a IMP. So IVMP, that is the PV voltage at which point? At maximum power point. Maximum power point. IMP, that is the PV current at maximum power. These are the four basic parameters which are involved in case of fill factor. Because you can see VOC, it is always greater than the VMPP. So if I'm operating at VOC, what is the magnitude of current? Anyone? If suppose I'm operating at VOC, the magnitude of current, the value of y-axis at x-axis, how much it is? 0. So we cannot operate at this point, right? So ISC is 0 at this point. However, if I'm operating panel at this point, then the VOC, that would be 0. So these 2 points I cannot operate. I cannot operate my panel on these 2 points. So where I will operate? I will operate where I can obtain maximum possible voltage and current. So this is the operating point of a PV. Operating point of a PV panel. Now, this is the operating point.
So, like how the zero keeps that? Explain that again.
In x-axis, what is the value of y? What are the coordinates at this point? VPV, 0. The coordinates at this point. 0, ISC. There is no value of y in this case. There is no value of x in y-axis. There is no value of x in y-axis.
So at starting, no, sir, like at starting, the value would be 0 only, no, sir.
Yes. Now slowly, because in starting, either it will be, so in starting it is acting as a open circuit when you have not connected any load to the PV panel. Suppose I have PV panel or PV module, I have not connected any load. So it will supply which voltage? VOC. Because current will not flow, because circuit is not closed. So it will operating at this point. But at this point, ISC 0. Are you able to get it? So what it would be the fill factor now? If I am going to derive the fill factor, what is fill factor? So fill factor, the value at operating point of a PV array or MPP point, that is VMP multiplied by IMP and divided by, what is the value? VOC multiplied by ISC. Because VOC and ISC, these are the 2 maximum possible values. Maximum possible values means at axis and y-axis. So this defines the, generally we used to write VMP. If suppose I wanted to write VMP, generally we are considering 20% losses as somebody told me. So generally the fill factor, it is 0.8 to 0.85. So if I'm going to calculate VMP, what I will do? 0.8 multiply by VOC. If I wanted to calculate IMP, what I will do? I will take the 0.8 multiply by ISC. This way we used to define these this fill factor. So somebody, if it is showing or it is telling you what is the fill factor of a PV panel which has been connected at the charging station, right? Whenever you are going to buy these panel, you have to look into the fill factor. Different OEM, they have different fill factor for each panel. It will depend what is the voltage at MPP, maximum power point.
Sir, I have a question. Yes. PV panel current is also DC, and EV get in DC or AC?
PV panel is DC, and then
EV is a EV battery or get DC or AC?
DC.
Okay, but it's also DC to DC converter.
Yes. In between, we are using DC-DC converter. We are not using some other converter. Because if you want to charge from PV, then obviously DC-DC converter will be required, not DC-AC or some other converter.
Okay.
Yeah. So what is now the obtainable power, right? What is obtainable power now? This is the installed capacity, 10 kilowatt, which I told you, that is installed capacity. But if you talk about the obtainable power, What is obtainable power now? Obtainable power. How much power we can obtain from this panel, that will depend on what is the value of IMP and what is the value of VMP. Correct? You cannot say we can obtain a power like VPV into IPV. That is not the power in this case, because under different conditions you have seen the curve. So when we are operating at maximum possible voltage, current is 0, and if we are slowly increasing, the magnitude of current would not be the maximum. So we have to operate at this point so that we can get the maximum current as well. Right? Maximum current as well. So if I'm writing now, this is all about the one panel, right? This is one panel or one module. Now, if I have various modules which are connected in series, then how do I define the open circuit voltage and short circuit voltage or whatever the value? So PMP generally we are presenting as a VMP multiply by IMP, and what we have to do, we have to multiply by number of series panel and number of parallel module. So NS, it is representing number of series modules. NP, it is representing number of parallel modules. P, it is representing the number of parallel modules. Okay. Any confusion in this? So how do I write VMP and IMP? VMP and IMP, I already told you. If I wanted to calculate VMP, the fill factor, suppose it is given 0.85. So what I will do, I will multiply by 0.85 and by VOC. If I wanted to calculate IMP, immediately I will multiply by fill factor and I can calculate the value of, and I can put the short circuit current. So these two parameters, open circuit voltage of the panel and short circuit current capability of the panel, that I have to know. Without knowing this panel, I cannot calculate the value of this, what we can say, the value of voltage and current. Right? So we have to take care, like what is the scenario, we are considering for this voltage and current. Any question on this? Generally, typical efficiency, if you consider cell efficiency, right, of a PV panel, that is not more than 7 to 21%. Cell efficiency, I'm not talking about the fill factor or some other terms. The cell efficiency of a PV panel, that is 17 to 21%, very low. Now, people are, these chemistry persons and material people, they are continuously doing research on this cell so that they can increase the efficiency, directly from 17 to, from 21% to 30%, 35%. They are continuously working to increase this efficiency. And this yes, this is one of the important area, right? These device people continuously working, material people, so that we can increase this. This is very important to increase the efficiency, because we are installing a 10 kilowatt panel, but we are not getting the maximum power from this 10 kilowatt panel. We have to be careful while we are. So what I will do, I will take a 15-minute break here and see you at 9:05, and then after 15 minutes. Okay, then we will discuss one hands-on problem based on this module. I'll tell you, we have to install a solar charging station of 30 kilowatt and now derive this IMP, ISC, different value of current and voltages. See you after 15 minutes. And here we can go with this particular problem, which I can share with you. So as I told you, we are going with some hands-on, based on this design of this solar power station, I would say, charging station. So power plant for charging station, right? So here we have design a 30 kilowatt capacity of solar power plant for charging station, the open circuit voltage and short circuit current rating, right? Short circuit current ratings of one solar module. Try to see. So what I will suggest all of you, kindly open your notebook and try to solve this particular problem. Right? I have given you the mic access. If you have any question or any doubt, you can ask me. I'm giving you this problem to you to solve and let me know the answer. So one solar module which are rated at 32.8, right? 32.8, and the current is 8.3. Also calculate the number of series and parallel modules to develop a solar-based power plant. Consider a factor of 85%. So what is this? This is nothing but a fill factor. This is fill factor between the open circuit and short circuit values. The load voltage requirement is 700 volt. What do you mean by load voltage? Means a battery voltage. We would have a battery which is giving or which is having a 700 volt. So we know we have to generate a total voltage from this 30 kilowatt capacity, that is 700 volt. Right? This voltage we have to achieve from this power plant. Can you solve it? First, try to write what are the parameters which are given in this question. Try to first write what are the parameters which are given here. Anyone?
30 kilowatt.
30 kilowatt?
No, 30 kilowatt on 32.8 voltage. So
Yeah, that is the module rating. So this is the module rating which is given here.
calculate the number of series and parallel module.
Yeah, we have to calculate that series and parallel module.
Yes, sir. Yes, sir. We can.
Yeah, try to calculate it.
How to calculate the fill factor is
85%. Fill factor it is given 85%.
Sir, the VMP voltage is 27.88.
27.83. Yeah, you can calculate VMP as well as other parameters.
Okay.
Yeah, try to calculate it. So for one module, right? For one module, the parameters VOC, that is 32.8 volt, and ISC, that is given as a 8.3 ampere. Now to calculate VMP, that is really important, right? How do we calculate it?
Sir, 21 panels in series.
21
Panel in series.
in series, yes. Very
And
good.
five panel in parallel.
Yes, yes.
That
Almost
means
5. Yeah. So
almost five. Almost
yes,
five panel in
yes,
parallel.
yes, you are very correct. So for one module, VOC is 32.8 and ISC that is 8.3 amps. Now let's discuss this VMP. So first we will try to calculate VMP. How do we calculate? The fill factor is given. Fill factor is given 85%. So VMP we can calculate 0.85 multiplied by VOC. So what is the value of VOC which is given? VOC is 32.8. So we can calculate that is 27.88. Now what about the IMPP or IMP? IMP that can be calculated as 0.85 multiplied by 8.3 because 8.3 current that is given here. Right? 8.3 ampere current is given. So that is 7 ampere, almost 7 ampere if I'm not wrong. Okay. Now total capacity, installed capacity of a plant. And try to keep it in mind. IMP is the current of one panel. So installed capacity that is IMP. So installed capacity, what is the installed capacity? 30 kilowatt. And what is the voltage? Because P is equal to V into I. So you have to put this total voltage. So total voltage will be 0.85 multiplied by 700. Okay? So IMP of a total installed capacity that we can calculate 50.42 ampere. Ampere. So we can calculate the series module NS. How do we calculate NS? NS basically it is giving the voltage. It is increasing the voltage. So we have total voltage that is 700 and the voltage by one panel that is 32.8. So what is this? Can you calculate 700 divided by 32.8? Can you divide it? It is given around 22. We can have like 21 point some value will come, 21.34. So this can be say that we have to go with the higher value. So let's suppose 22 panel that would be connected in series. Now IMP, how do we calculate IMP? And IMP we know, and we have this current IMP current, right? So NP can be calculated as a total current IMP divided by. You can take IMP or ISC, whatever the value you can consider. So IMP, total IMP, how much? Total IMP we have calculated 50.42. 50.42 divided by, what is ISC? 8.3. Can you divide these values? Can you divide these values?
It's 6.07.
6.07. So it is equivalent to 6 panels. Right? It is equivalent to 6 panels. Now, if I wanted to verify it, how do I verify? How do I verify it? So PMPP, I already told you. What is PMP? So PMP will be 0.85 of VOC, right? And multiply by 0.85 of ISC. Then we have parallel module and then series module. So this VOC, what is the value of VOC? What is the value of VOC? 32.8 multiplied by 0.85. What is ISC? 8.3 ampere. And number of series module, number of this parallel module, that is 6, and number of series module which we have calculated, that is 22. Can you calculate it? So this is verification. Do we really get this power or not? Right? Because we have to design it, the installed capacity is 30 kilowatt. But what is the PMP? Right? What is the actual power which we got from the solar panel? Solar module, I would say. Can you let me know? Can you calculate 0.85? Huh?
89.83.
89? 25 or what? Let me
6 kilowatt.
0.85.
5.96
25.96
kilowatt.
25.96 kilowatt. So you can see the installed capacity, or you are talking about the 30 kilowatt charging station, but the maximum obtainable power. This is obtainable power from the charging station. From the PV based charging station, I would say. PV based charging station. Correct? This could be equivalent to 26 kilowatt, not more than that. So if you are installing a 30 kilowatt, apart from losses, it's not mandatory, like if there are losses, then only this power will be reduced. No, this is due to the operation of the panel, as we are operating under open circuit condition, so there is no current, but as soon as this point is moving from open circuit to MPP condition or MPP point, the total power is going to decrease from installed capacity. So installed capacity, it is simple multiplication of open circuit voltage and short circuit current. But actual voltage, that is the multiplication of IMP into VM. Any confusion in the design of this solar plant? Suppose I have given some data and I'm asking to design a solar plant. So this way we will design.
So I went out that installed capacity is 30,000. How it frames. Can you go back to the previous slide?
Yeah, sure. Yeah.
IMP that's 30,000 divided 0.85 into 700. What is the formula?
So this is nothing but power is equal to VMP into IMP. Sorry, P is equal to IMP into VMP. So here you can see VMP we have considered. This is simple P equal to V into I. Nothing else. But if you are calculating IMP, you have to take VMP here. And what is VMP? 0.85 of VOC, total voltage. Because here we are talking about the total power. We are not talking about the only power of a single module. We are talking about the power of a total module.
But how the 30,000?
30 kilowatt that we can consider. 30 kilowatt that is coming from here, no? 30 kilowatt capacity of a plant. So you are taking total capacity, out of which how much power we have to deliver. So current will define how much current we are taking from this.
So can you write the formula for IMP? How it will be derived?
So IMP you can, what I told you, this PPV power, which is PPV, that is 30 kilowatt, 30,000 watts. So PPV will be IMP into VMP. This is the formula. So IMP we have to calculate, PPV it is given, VMP we can replace by 0.85 multiplied by IMP. Are you getting my point?
Okay.
So now let's talk about the concept of MPPT. I used